Okay, go ahead and graph. F of x equals x squared. When you think you got the graph, type it in your calculator and check it. Because the only way you know how to graph this function right now is the same way you do any function. You get a t-chart out, and you start plotting points. What my objective for today is to see that you be able to graph this without always having to do a t-chart. Now, if I put 0 in, I get 0 out. I put 1 in, I get 1 out. I put 2 in, I get 4 out. Put 3 in, I get 9 out. Is that a good representation of my data? What do you think, Maddie? Did I do a good job of graphing it? Just looks like this, connect the dots. How do I graph the other side? Okay, so -1, I get +1 out. Okay, -2, I get +4 out. -3, I get 9 out. Alright, this is what we call the parent function for a quadratic. This is the shape you're going to have to draw when we're transforming quadratics. When I mean transforming them, today we learned how to stretch them, compress them, reflect them, and translate them up and down. Horizontally stretch them, vertically stretch them. Horizontally compress them, and vertically compress them. That's translated. Okay. All right. Without using the t-chart, make your best guess of what y equals. And I put y equals here. I haven't changed my lesson plan from last year. And last year I didn't want to, I should say, freak out some of my regular Algebra 2 students by putting that f of x in there. They would shut down before I even started. Okay, the f of x is the same thing as y, it's just in function notation. Okay, y is in the format of what you're used to seeing, I realize that. Okay, but I want to know what this is right here, and then describe the transformation that is occurring. There is only one way for me to know how you've transformed this thing. Is this going to transform anything? What's going to happen to it? No, the question, okay. If you only put one parabola on your graph, I will never know if it's stretched or compressed at all. Otherwise, okay, you flip up your beautiful graph, okay, and your beautiful graph, everybody look like this. And artistically, you're going to say, oh yeah, I vertically stretched this. And I'm going to say, no, you didn't. Just because I can argue with you very well. Okay? But if you come up here and you show me, okay, here's normal. And this is what you're going to have to realize. If you don't know what normal is, do a t-chart every time. Because your normal better be on. Okay, it better not look like a V. Okay, it better be uniformal. Why did I make it dotted?
Because it's the parent
function.
function.
The parent function. I want the actual function. And if you have to do a t-chart, I suppose you do. Okay, you come up here, x, you get y. You plug in 0 and you get 0 out. It has the same vertex. Okay, plug in 1 and I get 2 out. Plug in 2, okay, and I'm going to get 8 out. I plug in 3, okay, up there and I get 18 out. This essentially is, and this is how I always look at it, that 2 is like a stretch factor of rise 2, run 1. It just stretched it inside like that. I am fine with you not doing a t-chart if you put a parent function down. If you put no parent function down, I need a t-chart that has at least 6 to 8 values on it every time. Yeah. And that, you know, if you're doing 30 problems, that's a lot of work. Otherwise, all you have to do is come up here and draw quick this way and a quick inside the normal function. But I do want the vertex always labeled.
So it doesn't have to be exact.
It doesn't have to be exact, but it does have to be, I did have people doing this last hour. Why is that green one not so good?
Because it's way different.
What do you mean way different?
It's way different.
If I pull out to this red one right here, why does that green one look crappy?
It's lopsided.
What do you mean by that? We gotta talk mathematically. You're artistically explaining. Okay, what's that mean?
There's like definite points of where it's going through.
Yeah. What do we call that if it's supposed to be uniformly the same on both sides?
I said symmetrical.
There we go. There's supposed to be a line of symmetry here. Okay, when I looked at, okay, this red one right here, I had a line of symmetry that eventually you're going to label and draw in, but I'll wait to label and draw it until I shift it left or right. Right now, the y-axis is my line of symmetry, which is x equals 0. Okay, and you can quote me here in about 5-6 slides. Okay, I will come back to this, and I'm going to shake my head and say, no, you didn't graph it right, because I shifted it left or right, and you forgot the line of symmetry. Okay, I'll say you'll do that now, so the stubborn people will remember not to do it.
We have to put the origin of it.
You always have to put the vertex.
Yeah.
Okay, it is the origin this time.
Do we have to put other points on that?
You do not. You do not. Okay?
Thank you.
Yes, I'm saving you some time. But I do want you on this one now to verbally describe this first, then graph it, and then finally use your TI calculator to check it. Okay? This right here is a function. Negative 2/7 x squared. Describe the transformation occurring first. And I'm going to give you a hint before you graph it. It's kind of like you and I. We're very similar to our parents. If our parents are negative people, a lot of times you are as well. You're translated, you're stretched, your reflected function, all of those things need to be similar to the parent function. So if the parents are going up, okay, so is the transformed function. If the parent's going down, so is the transformed function. They resemble each other. You can't just draw, oh yeah, I always draw a parent function like this. And I'll do that 15 times, and then I'll just, do my homework assignment. No, this has to show a parent function right here going upside down. Why do I have to draw that parent function going upside down?
Because
What
Because-
negative?
It's negative.
What about negative? Aaron? There, that's what I wanted to see. I wanted to hear the math. Because this negative right here reflected over the x-axis. Okay, that was reflected over the x-axis. That was what the negative did. What did the 2/7 do to the function?
Compressed it, vertically compressed it.
They vertically compressed it. And you see, here's the argument. Did it vertically compress it, or did it horizontally stretch it? The difference is this. If I wanted this thing to be vertical, I would have took this 2/7 and times the parent function. Do you see how that x squared is the parent function? I would have times it by 2/7. That made a vertical. This right here, okay, made this a vertical. Okay, it's less than 1. Compression of 2/7. If I wanted to talk in the terms of horizontal, okay, I couldn't have put the 2/7 here. I would have had to put the 2/7 right there, which would have essentially put the 2/7 inside there, which, are you really doing something by a factor of 2/7 now? Well, that's how we're going to talk about it, but what it actually is occurring here, 2/7. What do you do if you take 2/7 x squared? 2/7 times 2/7. This is 4/49 x squared. This is not my f function. This would be like my new transform function. Now here, put your thinking caps on and verbally listen to this. This function right here and the two functions I circled have the exact same graphs. You type them in the graphing calculator, you'd get the same thing. However, this is how you say this one. This is vertically compressed by a factor of 4/49. This is horizontally stretched. It's horizontally stretched, vertically compressed. What factor is this horizontally stretched by? Horizontally stretched. And some of you are saying, how can that be stretched? It's 2/7. Whenever you do things horizontal, what do we have to do to the factor? Reciprocal. Okay. It's a horizontal stretch of 7/2. 7/2 is 3.5. So that's bigger than 1, so that means stretch. Alright, I'm not asking you to wrap your mind around that too much, but in the essence, when it comes down to it, your graph right here, if you forget the worst case scenario, I can't remember, is this wide or is this skinny? Remember 2/7. If I went down 2/7, down 2/7, is that going to make it wide or skinny?
Wide.
Now that's a heck of a lot wider than it really is. Go ahead and put it in your graphing calculator right now and see how wide. I mean, look how wide I'm making it right now. If I was to do that down 2/7, down 2/7, I mean, that's a line if I do that. But down 2/7 at least tells me it's wide, it's not skinny. At least telling me it's vertically compressed. Graphing calculator tells me, well, first thing I need to do here is get my negative x squared. Now watch how I put that in my function there. I put negative 2/7 x squared in there. Be careful on how you type it in there, because that may make the function wrong if you don't type things in. When I graph that, I mean, look at my graph and look at the graphing calculator. And yes, I do have it still on a square window. So it's not being stretched out any, and it's not that much bigger. Okay, so I'm looking at a graph that's probably, okay, like that. Is it down 2/7? No. But I'm telling you right now that down, if I forgot tomorrow, if I gave you a quiz tomorrow, and you all of a sudden forgot, oh crap, it's 2/7 wide or skinny. No. Down 2/7 tells me it's wider. So it helps me remember if it's a stretch or a compression. Okay? Alright. So our dance so far, we know how to do this. Oh yeah, we know how to do this. Okay? What else is going to have to come to our dance? Now when we get that function dance out?
Parabola.
Well, we got a parabola. What's our dance going to look like though? We got to have some more moves. This is kind of a boring one that we have next week during homecoming. We have this, and we have this one, we have this one, and then, no, we're not going to quite go that way yet. We'll get this one here eventually. Okay, but, okay, what does this plus 2 do to the function? Okay, go ahead and write down on your graph. You don't have to graph this one. I just wanted you to write down. What is the verbal transformation that is occurring to this x squared plus 2? Then type it into your graphing calculator and check yourself. Flip up your board once you got it written down so I can see what you wrote. Ideas are good. Math. Verbiage is not good. I still like you can write that better. I'm asking for the transformation that occurs. Up. Moves up is not a transformation. Slides is not a transformation. Shifts is not a transformation. Move up is not a transformation. Transformations, I believe we can reflect. Okay, we can compress. We can stretch. Okay, and we can translate. This right here, okay, translates it up to your graphing calculator. Okay, should have shown this. Now notice what I'm going to do. My parent function moves with the translated function. The parent function needs to be, okay, right there. But however, did I stretch this function any?
No.
No, so the actual function ends up getting written right over top of the parent. You didn't have to do the parent, but I wanted you to see that you start with the parent, and then you translate it first, left or right, up or down, okay, and then you stretch it. Okay, I always start with my moves. Translate it left or right. Okay? Maybe that's because the dance looks the best in you. Move this way, move that way. Pretty good moves, aren't they? Well, I'll have to skip that one. We ran out of time last hour, and that's a good one to skip. We shouldn't need a TI. I want you to, without your TI, go ahead and write down first what transformation do you think is going to occur. Then go ahead and graph it. You got that written down and graph, flip your work up so I can see it. Maybe you look like you're in trouble back there. Nastasha, are they causing problems back there? No, they're okay. Now graph it. Your first word on this. It's not Englishly written. Grammatically. We should always shift it first. Okay? So that transformation right here that occurred. Translated. Down. 4. Right, so we went down 4. I labeled my vertex.
So did I.
Of course you did.
I did too.
Of course. Everybody never forgets those little labels. Okay, I got my label for my vertex. And then I noticed right up here, is this thing going to go, is this parabola going to go up or down, Ben?
Up.
How'd you know it was going to go up?
Because it's not negative.
All right, so this part right here told us that this thing's going to go up. So my parent function is now, and I do appreciate those of you that draw the parabola throughout the entire graph. Okay, make sure it goes all the way to the end. Okay, and then the last part is, well then what does this 2 do to the function, Tim? What would we have for this 2? How is it affecting this graph?
It stretches it vertically by a factor of 2.
This does. This vertically Okay, and vertically, I can't remember if it's stretch or compression. Well, if it's bigger than 1, it's a stretch. Stretch by 2. Does that make it skinny or is that going to make it wide? Well, if I can't physically, in my mind, wrap myself around seeing it stretch it, then I'll go up 2 over 1, up 2 over 1, and I can kind of see, okay, that graph along this beautiful line of symmetry.
Are we just guessing what the
Okay.
parent function looks like? Or
You are guessing its width because you're practicing every time trying to get that parent function the same every time. So if you don't know what a parent function is normally, then everything's going to be wrong, skewed around it. You know what I'm saying? If you make the parent function wide, everything's going to be wider than normal. Okay, so that's why I wanted you to graph the calculator, I wanted you to do a T-chart, so you can kind of see what the what the norm is. Okay? It's not a big deal, but for the most part, you guys need to have a fairly good idea of it. All right, how are we doing here so far on a scale of 1 to 5? Okay, so we've talked a little bit about going up and down translations. Okay, skinny, wide, okay, that are in there. Okay, what I want you to do is with you and your partner, I would like one person to graph. Before you graph, though, tell me the transformations that occur here. And the other person to do that one right there. Tell me the transformations that are going to occur. Now, some of you are looking at me right now. Those are the same numbers. Same graph. Are these graphs going to be identical?
No.
No, this right over here is a vertical stretch or compression. This right here is a horizontal. Okay, go ahead. Do your transformations. Okay, and then check your neighbor. Flip boards and have them check with you. If there's 3 in a group, then you just kind of, 2 of you do one and 1 of you does another.
you watch me. I'm gonna get it ready.
Such confidence back there, Seth. How do you deal with all that confidence? I'm sorry I put you with those 3 girls. If I would have just known that from the beginning. You have this quiet group right up here, right? I don't know how you keep them in line, too. These girls are so obnoxious. That's not a very good description of functions transformation. Okay. Of how much, and that's all that's happening. If you did the first one, I think there's 3 transformations that are occurring. Maybe the second one. Have your neighbor check in. those of you that graphed it, regardless of what you did right here, okay, did you notice that they both translated up 2 units?
Yes.
Okay. Okay, both of them are translated up 2 units. Are both of them reflected right here? Okay, over the x-axis.
No.
This one has a negative.
Yeah, but it's squared, so it becomes positive.
Alright. This problem right here, in simplifying it, we have negative 3/8x times negative 3/8x. This right here is horizontally, okay, being stretched or compressed. Okay, and this ends up turning out to be essentially 9/64x squared plus 2. If I was to type in that into my calculator, and I typed the original one in my calculator, they should give me the same functions. Okay. However, how I say the second one right here is it's translated up 2, okay, and then this 3/8. What does the 3/8 do to the function? Does it compress it or does it stretch it? Well, my graph
Horizontally stretched.
horizontally. We got to say that first.
Vertically compressed.
No, it's a horizontal because it's with the x. It's horizontally,
Stretched.
and it has to be the reciprocal. The reciprocal is 8/3. Is 8/3 a stretch or a compression? 8/3 is bigger than 1. So horizontally, okay, stretched, okay, by 8/3. This then has the same vertex. The parent function for this one, okay, goes up. The parent function for this other one, first one, goes down because it's reflected over. 3/8, okay, rise 3, run 8, okay, made this thing go wide because it was vertically squished. Okay, so I'm pushing in on these arrows, making it wider. Okay, this one right here, okay, I have to do the same thing, but 3/8 is still wide, but it's actually, this one's really wide because 9/64 vertically compressed is the same as horizontally stretching it by 8/3.
Okay, I have 2 questions, so I'm going to tell you them both.
Yes. Okay.
Okay, my second one that I want you to answer.
I want the first one off first.
Okay, well, I'm not going to give it to you first.
Alright, I'll get the second.
Why can't you just divide it by negative 3/8? And then my first one is, why is it horizontal? Because
It is horizontal because when I take a function and I multiply this by, okay, negative 3/8, that goes into that function right there. That went into that function. Okay, and squared the entire part of it.
that does not you get over.
How do I get vertical at it? I didn't. It's horizontal. It's horizontal because anything that goes into the x component, x's are horizontal. Anything right over here, what I did here is I took this function right here and I times it by the whole function, this x squared. I took that x squared right there and I multiplied it by 3/8. In fact, negative 3/8, but you know, I'm timesing this whole function by 3/8. This part right here, I'm just timesing the x by 3/8.
Okay, so then why can't you just divide it by negative 3/8? You know, like
You-
you did earlier.
1 over 3/8 is the same as 8/3. I don't divide, no, I don't divide this to get over here. No, I'm multiplying both sides by
No,
3/8.
I'm talking about. Okay, so you know how before when we had like absolute values?
Yeah?
No.
Factor it out? Is that what you're talking about?
Okay, yeah, we had to factor it out. Why can't
Because there's
you-
nothing to factor out of that. You have to do orders of operations for one in order, and there's nothing to factor out. You have to square first and then factor it out. Absolute value bars were not, they were just contained and you pull it out. They are different in that little bit. This is where absolute values do differ from the quadratics.
Okay.
Don't know if I answered your question, and I don't know why it was so funny, but we'll let that be. All right. There's your next function. Okay, whether you write it in function notation or not. Okay, let's forget about the TI. See if you can tell me, where is the vertex going to be in graph it without the TI? Use your TI just to check. Enough sleeping.
Yep, that's enough.
Sorry. I was distracted.
You were.
Oh,
I will tell you one thing right away. Orders of operations tell you to deal with parentheses first. You deal with the x plus 2 first. You can't square it first. What does the x plus 2 do in our transformations? Oh, there we go. Okay, we finally get a move. Left and right. Does this move it to the right or does this move it to the left? And this goes back to the absolute value functions. When I was doing absolute values, y equals a times absolute value of x minus h plus k. When I did that, my vertex was always at h comma k. I'm going to do the same thing right up here. It's going to be y equals a times x minus h, the quantity squared. No absolute value, but the quantity squared plus k. And the vertex is still h comma k. To find the h term, just like I said, the people in the jail always look the opposite that they were. The squareds are always the opposite of what they really are. So you always have to take this x plus 2, set it equal to 0 to see what it really is. My vertex, for this right here, goes left 2. There's my k, up 3. Left 2, up 3. Go ahead and graph your equation here. The only transformation that occurred here is a translation left 2, up 3. Done.
Pretty good.
Okay, let me see it. Wrong.
You don't need a pair function because
You're correct. You go ahead and correct.
I knew that.
You're incorrect. You're incorrect. Incorrect. You're not very stubborn learners. Almost.
I don't label my vertex.
I know. Besides not being able to draw, it's still wrong.
What?
Sydney.
Me?
Almost. No? No? Yes. Very good. Close. I guess you can't really mad at that answer.
Not a good
Don't prove her wrong. Well, bitch, she'll spin a pop all over, so watch out. Oh, close. You're getting there. You're getting there.
Wait.
Guys,
Here.
for 1,
What about this?
that has to be labeled.
What about this?
Okay, for 2, look at this.
What about this?
Okay, you can't draw crap like that because you need to have the line of symmetry. Do you have it labeled?
Yeah.
I put it dotted just so you know it's not part of the graph. It's just something that helps me draw symmetry. X equals negative 2. Okay, so let's get rid of this crappy thing right here. Okay, we have negative 2, 3. Okay, and here's normal going up.
You got some.
Do I need normal? No, because this has, no compression, no stretch to it. Okay? With that line of symmetry there, I can see that it is symmetrical on both sides. You can label it x equals -2. That's a nice learning tool that leads into how to find the equations of those later on also. Alright, how are we doing here so far? We got about 15 minutes left here to kind of conclude our little dance. Okay, scale 1 to 5, how are we doing? Fives, fours, threes. Oh, I worry about the threes. Okay, let's see if we can get you back up. Okay? Describe the transformation first.
Does it say 0?
This says y equals. Okay, if you don't like the y equals, I'll put it in function notation, f of x. And again, I can put any letters here. I keep on using f. Okay, but f for function, they always do it. And call it h of x equals 4 times x plus 1, quantity squared, plus 6. Orders of operations tell us to translate it first. Find the vertex through the translation. Then reflect it. Then stretch it. Then compress it. Horizontally or vertically.
Aren't the parentheses the absolute value?
They are not. It's not an absolute value function. It's a quadratic function. Does it act like an absolute value? Very simple. Yes.
You know, how the absolute value is able to translate the vertex left and right.
This has nothing to do with absolute value. Let's go back to, please, just kind of go. Find the vertex.
Did you say yes?
Now, since this is positive 4, we know it has to go up, but that 4 is vertical because essentially I multiplied this squared component right there. The parent function x squared, I multiplied it by a factor of 4, which vertically, since it's bigger than 1, stretches, okay, that thing by 4. Before I do any graphing, I get my line of symmetry in here at x equals -1. I know it goes up, so I need a parent function going up. And I know vertically stretching, maybe I can't see that that's going to make it skinnier. And I forget this tomorrow on the quiz. So I go up 4 over 1, and yes, that does confirm that that's approximate. You guys do realize that 4 over 1 is really not showing its true width.
Yes, sir.
Have you guys got that part? Because I don't want you walking into pre-calc saying, Mr. V.O. Cross there and saying, Mr. Johnson told us that that was the slope. The slope is a constant amount. It is a parabola increasing at a constant amount. That 4 over 1 thing is only helping you see it's vertically being stretched, that you have to put it inside of normal. That's the only little mnemonic device I gave you to help you remember wide or skinny. Okay, so there we go. Okay, because we are running out a little bit of time here, I just want a conversation with your neighbor. Some of you have too many of them as it is already, but tell them how this equation differs from that one in a verbal transformation. There's your new equation. Verbally tell them how y equals -4 times x plus 2 squared plus 6 is different. Help you, I still need to hear from.
Upside.
I don't like, it's upside down. What does upside down mean? Oh, it's flipped around. It's reflected over the x-axis. Okay, that's your transformation. Reflected. We're not done, guys. This is just getting running down here. Okay, now here's the most important part right here. The last two things. Okay, I have this one right here. I want person number 1 to graph. Person number 2, I want you to graph. Okay, 2/5 x, the quantity squared plus 6. First of all, am I going to get the same answer out of both of you? No, I am not. I am not going to get the same answer out of both of you.
We have to,
Okay, I want, the graph and then the domain and range.
Yeah.
You do not. I want the graph and then the domain and range.
Domain and
Okay,
range.
ready, set, go. You got 90 seconds. Go. I hope you all realize that all of your guys' vertexes will be at 0, 6. Both functions are translated up 6. Do both parent functions go up or both parent functions go down? Both of you have yours going up. Okay, good. So I'll continue to. It's a little wider than normal supposed to be. So they're both up and they're both wide.
Why?
They're both what?
Why?
Wide.
Oh.
W-I-D-E. Wide. True or false? Are they both wide? Do they both have the same width?
No.
Okay, which one's wider? Okay, the first one on the slide or the second one? Second one? Okay, I would agree because this right here is 2/5 x times 2/5 x. This is the function that is horizontally stretched by a factor of 5/2. This is said, even though this is how I wrote it, okay? It was originally written as a horizontal stretch of 5/2. Okay, I am pulling on that thing horizontally, okay, by 5/2. Okay, 4/25 is getting this thing way out here, like that. Okay, this other one that I have right over here, this is called a vertical because it's just timesing the parent function x squared by 2/5. This is a vertical, okay, compression. If I'm vertically compressing in this direction, it still makes it go wide. Rise 2, run 5. Rise 2, run 5. Okay, but we got to realize that 2/5 is a lot skinnier than 4/25. Okay, scale 1 to 5. Let me see how you comprehended what I just said. I didn't write it all down, but it was a verbal confirmation. Question, Maddie? Five halves is the horizontal stretch. A stretch horizontally pulls on it this way. You know what I'm saying? It's like a rubber band. You're pulling out, I'm stretching it horizontally. This way, I'm squishing it in here, which makes it fatter too. Okay, because horizontal stretches and vertical compressions essentially make your graph go the same way. That's how I said the stretch occurred right over here. I said it occurred right here by, okay, a 5/2 stretch. Even though 2/5 was there. It's a stretch of 5/2.
Okay, so you just keep the two fists, but like if you're
You
explaining
gotta
it
know
for
the
like-
verbalage is whatever goes in here was the reciprocal. The reciprocal of 2/5 is 5 halves. 5 halves is bigger than 1, so that's a stretch. It's in here with the x, that's horizontal. Horizontal, bigger than 1, stretch, 5 halves. Okay, I should go with it. Okay, that's reciprocal. So,
For the number 2, it's horizontal stretch by 5 halves. But why isn't it horizontal stretch by 25?
because this is what's happened vertically to it. I can talk about how vertical and horizontals give you the same graph. But in the original equation, we were talking about a horizontal stretch. This equation right here would essentially give me the same thing as this horizontal one did, but vertically stretching.
So you
Or
call the
compressed.
top one vertically compressed, but the top one horizontal.
Yes. Yes. Good. All right. I'm going to leave this for right now. Yes.
Would you like graph that specify the exact points, or we just?
No, see, that's the part. If I wanted exact points, I'll say do a T-chart, which we're not going to like, or use your graphing calculator. This is just, I'm learning the characteristics. That's all you're doing right now. If you know the characteristics of what's happening, it's going wide, it's going skinny, it's really more important than your beautiful artistic work. Okay? And in order so you get something that's actually halfway decent, I need that parent function in there so I can see if it's wide or skinny. All right. I'm going to skip this. Remind me tomorrow that I got to talk about how to find slope given another point besides the vertex. Okay? Remind me tomorrow to do that. Your assignment for tonight, okay, is 1, you need to go over there, grab a textbook back there that says Algebra 2 on it. Okay? This textbook, eventually, I'll get you an online code that you don't have to take your textbook home with you anymore, but you will have to bring it to class. Okay, right now, that's your textbook for tonight. Yes, I know this section 2.1. I know the numbers are out of order. This is a learning technique of I want you to do these problems in this order because I feel you'll retain it better. If I really wanted to save some time, I just would have put 1 through 38. That's a lot shorter for me to write. I can change it if you want. You can have it sticky note, do whatever you want with it, Abby. It's yours now. You took that book. There might be a possible quiz tomorrow on what we talked about. Okay, you know, sometimes there's homework quizzes. Sometimes, you know, I just have a quick quiz over what we talked about. The Chapter 1 test, as I said, I haven't graded that. That was just a little note to me to remind you. Okay, graph paper. Okay, if you do not pick up graph paper here, because you are going to have to graph like today, graph paper, there is some on my website always. Okay, just a template there that you can always print out. Okay, the graph paper should be some still down there if you dig around. Please put your whiteboards back. And as I always do, I will post today's lesson because I thought your guys' hour went the best out of everybody's. Okay, and I got everything covered. Okay, last hour I ran out of time, so I will post